Okay, let's first talk about modeling. So modeling is the part where we look at an actual engineering system or a natural system and we try to model it as something simple. Okay, and remember, in this class, in pretty much every module that we have discussed so far, we have been doing modeling all the time. We have looked at physical objects, we have modeled them as particles, we have modeled them as rigid bodies. The only thing we have not done so far in this class is model them as deformable bodies, but that's something that you will get to do when you get to a more advanced class, where you study the stresses and the strain, and the rigid bodies will not be rigid bodies, but actually they will be deforming over time. So modeling is that aspect where we ask questions and we know that we can get answers to those questions by creating models of physical objects, either as a particle or as a rigid body. Now in this particular module, we are going to be doing something similar. So things that may not look like, maybe a mass or a spring will actually be modeled as a spring mass system. And in fact, that's one of the simplest models for studying vibrations that we can create. So take, for example, a car. Okay, so, we have a car and this car is actually moving over, some sort of bumpy road. Okay, so clearly the car is going to oscillate, right? It's going to go up and down. And we can model this whole thing as a mass. So this is the mass of the car with a spring, okay? And where would this spring come from? You have some suspension system in the car, and that suspension system could be modeled as a spring. And then you have your ground, okay? So which means that as this mass moves up and down, it does oscillation about equilibrium, and you have, some spring stiffness K. So you have essentially turned this car with suspension system and the wheels moving over a bumpy road into a spring mass system. Now, for the kinds of questions we want to answer, maybe this model would suffice, or maybe this model won't suffice, okay? Because the kind of idealization that we're making, won't give us answers that are accurate enough or reasonable enough that we need. So in that case, maybe we will add a dash part, okay, which will represent viscous damping, and we are going to do that pretty soon as well. So a large majority of the systems can be modeled in this way, where you have a mass, you have a spring, you have maybe a viscous damper, okay. Even the things that don't look like a spring at all can be modeled as a spring too. So take, for example, a rod, okay. So let's say we have a rod and you apply a force P, okay. That if you apply a force P, then there might be some elongation, of course, depends on what the material is. Okay, so let's say there's some elongation by amount delta, then P is proportional to delta, right? And that gives rise to the Hooke's law, which says that P equal to K delta. So the stretch in the rod is proportional to the force applied, and of course what this constant K would be dependent on what the length of this rod is, what the diameter is, or the cross-sectional area is, and what kind of material it is made from, right? And the material will basically give you something like elasticity modulus for that, and K would be dependent on all those, right? So this whole thing can be turned now into a spring, right? So you have a spring of spring constant K, which is dependent on, elasticity modulus, the cross-sectional area, as well as length. Now, if you take the same rod, and instead of applying a longitudinal force, you actually apply a bending moment. So if you apply a bending moment, then it's going to, let's say, and this is exaggerated, of course, I'm never going to bend that much, then due to the application of this moment over here, or, you could apply a point force P like that, and that would allow it to rotate as well. Now you could model it as another element, maybe a spring, or maybe a, simple massless rod with a torsional spring tied over here, right? And in that case, that the mass, the moment is proportional to the rotation angle. So let's say that is the rotation angle theta. And this is equal to K sub T times theta, where K sub T gives you basically your stiffness, but it's for a different kind of force. You could also take the same rod and actually subject it to some sort of torsion. So if you are subject to some sort of torsion, you might get another spring constant as a result of it. So, none of these physical objects over here look like spring, but they can be modeled as a spring, okay? If you want to make your life a little bit more complicated, you could do something like this. You could say, okay, I can model things as a spring mass system, but if I wanted to create a better model, I might add some inertia to the spring, right? So in general, when we create a spring mass system, we assume that this is massless. We assume that the spring is massless. But if you attach mass to the spring, which means that you add inertia to the spring, then the problem will become a little bit more complicated. Your model will be slightly more advanced. Similarly, if you look at the mass, usually we think of mass as just inertia, but now you can attach some stiffness to it. You could attach some stiffness to it, and if you attach stiffness to it, then there is some element of a springiness that comes into this mass as well, right? Which is what we've seen over here for these 3 bars. So these 3 bars, you would think of them as masses, but now they can also be seen as masses, which is inertia, plus the stiffness, which comes from a spring. So a lot of systems in engineering can be modeled as a spring mass or a spring mass and damping system. And we are going to basically look at all of those elements and see how we can obtain the equation of motion for them, as well as solve the equation of motion to get the displacement over time. So let's start by looking at a simple spring mass system and try to derive the equation of motion for it and see how we can solve for it. So let's say we have a spring of stiffness K attached to a mass M. All right. And we want to determine the equation of motion for this particle. So let's say this is the equilibrium position. So in this position, the spring is not stretched, it's not compressed either. And we will choose a positive direction of motion. So let's say towards the right is the positive direction of the motion. So we stretch it by amount x. So we will analyze this in a way similar to what we have done before when we did the kinetics of particles, by starting with the kinematic analysis. So we know the acceleration for this is equal to x double dot I hat. Okay, and if you draw the free body diagram, so you pick a different color, if you draw the free body diagram, this position, then the force that is pulling it back to the equilibrium is k times x, because it is stretched by amount x from equilibrium, which is also the position where the spring is not stretched. And then of course you have the normal reaction and you have the gravity acting downward. And of course in the vertical direction things are balanced and is equal to mg is not that important to us. So sigma f equal to ma. So some of the forces are minus kx equal to m times x double dot. Notice how I'm not writing I hat anymore because the positive and negative sign is taking care of the direction. So this gives us mx double dot plus kx equal to 0. And I'm going to divide by m and write this as x double dot plus k over m times x equal to 0. Okay, and that is what we call the equation of motion. So if I say give me the equation of motion, I'm not really asking for solution of x as a function of time, but really just this particular differential equation. So this is also known as second order differential equation, and this is also homogeneous. So let me write second order ordinary differential equation of homogeneous form. Okay, it goes by different names. You could also call it second order homogeneous differential equation and so on. So there is a particular way to solve this kind of equation, right? So let's do that. We know that we can solve this equation by assuming that x has a solution of the form, let's say e to the power lambda t. And of course, if it doesn't have a solution of this form, then we won't be able to solve this equation. So let's substitute that. So x is e to the power lambda t, x dot would be lambda e to the power lambda t, and x double dot would be equal to lambda square e to the power lambda t, right? So where lambda is something that we don't know, right? And t is the time. So let's substitute for these in the equation of motion, and we get lambda square e to the power lambda t plus k over m e to the power lambda t equal to 0. E to the power lambda t comes out as common, and this is lambda square plus k over m equal to 0. Now, of course, e to the power lambda t cannot be equal to 0, because if that were the case, then we will get a trivial solution, which means that this should be equal to 0. So lambda square plus k over m is equal to 0, and that gives you lambda as plus minus I square root of k over m, where I is the iota defined as I squared to be minus 1. So in this case, we get lambda to have two values because we essentially had a quadratic equation. By the way, this equation over here, as you may have seen before, is also called characteristic equation. Okay, so we have two solutions. Since this is a homogeneous equation, that means that a linear combination of the solution would also be a combination for this homogeneous equation, right? By the way, I guess you guys know why this is called homogeneous equation. The reason it's called homogeneous equation is that if let's say, there is a solution for x, then if you multiply it with a constant substitute in this equation, even that would be a solution. So for example, if x was given as some function of time, and that was the solution for this equation, then if you multiply it with some c, let's say cxt, and we get x prime as a result of that, then x prime is also a solution for this equation of motion. Okay, so this would happen only if, let's say, every term in here is either x or a derivative of x, right? Which is the case over here. If you have a constant term, then this would not be a homogeneous equation. If you don't have a term which doesn't have x or x dot or x double dot and so on, then it won't be a homogeneous equation. So what makes this equation homogeneous is the fact that if there is a solution x, you multiply it with a constant, then constant times the original solution is also a solution for this ordinary differential equation. And the reason it's called ordinary is because it's not partial, where you can have multiple variables. Okay. All right. So let's come back to, what lambda is. So lambda is this, which means that there are two solutions. Let's call it x1. So x1 would be e to power lambda 1t, where lambda 1 we can call is equal to I square root of k over m, and x2t, which is another solution, which is e to power lambda 2, where lambda 2 is equal to minus I square root of k over m. And since this is a homogeneous differential equation you're solving, and these two are solution of a homogeneous differential equation, which means a linear combination of these two is also a solution. So what's a linear combination? A linear combination of these two can be obtained by multiplying a with x1 and b with x2, where a and b are some constants, which we don't know what they are, right, at this point. So let's write x1 e to power lambda 1t plus b times e to power lambda 2t, and this is e to power I square root of k over mt is b times e to power minus I square root of k over mt. Okay, we also know that e to the power I theta is equal to cosine theta plus I sine theta, right? So e to power I theta is the exponential form of a complex number, and that's equal to a complex number given by this. So which means that e to power I square root of k over mt can be written as cosine square root k over mt plus I sine square root of k over mt plus b times, let me put this in the box, plus b times cosine square root of k over mt minus I sine square root of k over mt. Okay, so all I've done is basically just written e to power I lambda 1, e to power I lambda 2 in the polar form, and we get this, right? So now you can clearly see that we have cosine square root of k over mt here, we have sine square root of k over mt, and those two terms are repeated over here, which tells you that actually these two are also solutions to your ordinary differential equation. So let's say cosine square root of k over mt and sine square root of k over mt are the two solutions. So if there are two solutions, then a linear combination of them should also be a solution, right? And you can verify that. So if you take, let's say this and substitute into your differential equation, which is right over here, the equation of motion, you'll find that it actually checks out, okay? Same thing with this term. So we can say now that x can be written as, some constant c1, and I'm choosing different constant from a and b because I don't want to mislead you thinking that we have the same constant. So c1 times cosine of square root of k over mt plus c2 times sine of square root of k over mt. Okay, and at this point I'm going to start writing square root of k over m as omega n, and I'm going to tell you why I'm writing omega sub n. Okay, it relates to the natural frequency of the oscillation. So we'll make that substitution over here. So c1 times cosine omega nt plus c2 times sine omega nt, and that is a solution for your ordinary differential equation. Now we can simplify this a little bit further. So what I'm going to do is I'm going to actually divide by square root of c1 squared plus c2 squared. So let me do that first. And of course, since I divided, I have to multiply it too. So square root of c1 squared plus c2 squared. Okay. And there's another thing I'm going to do. So let's call this c1 and c2. So this is a right angle triangle. If this is c1, this is c2, then this is c1 squared plus c2 squared square root. So that means that this quantity over here is actually equal to sine phi, right? Sine phi equal to c1 over this. So this is equal to sine phi cosine omega nt plus, and this quantity over here is cosine phi, so this is cosine phi sine omega nt. Notice sine omega nt is the argument for the sine and cosine function, right? Times, and this quantity I will write as xm. So I'm going to write this first, x sub m. Again, why I'm writing x sub m is something that will become clear to you pretty soon. So x now becomes xm times sine omega nt plus phi, right? Because sine omega nt plus phi is nothing but sine omega nt times cosine phi, which is this, plus sine phi times cosine omega nt. So we get the solution to our equation of motion as this. Okay, now let's look at this. This is the solution to any ordinary differential equation that can be written in this form. And this form is also known as a standard form of a harmonic oscillator. Okay, and again, why it's called a harmonic oscillator is something now is clear to you, because what we have over here is a sine function, which is a harmonic function, right? So if you plot this, what does it look like? If you plot x as a function of time, so t is on the x-axis, x is on the y-axis, so we can see that at time t equal to 0, this value would be, so let me write that, at time t equal to 0, this x is equal to xm times sine phi, right? So we have some non-zero value at time t equal to 0, and then after that it basically follows a sine curve, right? So you can draw a sine curve, and clearly it is oscillating because this is a sine function, right? And of course, it can go back in time as well, right? So this is what continuous sine function that we're looking at. Okay, so what is the maximum value of x, right? The maximum value of x is going to be achieved when sine of something is 1, right? Maximum value of the sine of any degree, any radian, and any angle is actually 1, right? So that's plus 1. So maximum value of x is xm. So this is xm. This is xm. That's the maximum value. And that's why we're calling it x sub m. In fact, this is also called amplitude. So the maximum value of the x is called amplitude. So if you go back to your spring mass example over here, if you take this mass and you pull it to the right by a certain distance, let's say, and you pull it by, let's say, I don't know, we'll call it maybe 5 inches to the right, and you release it. So at time t equal to 0, it started this journey of when it was stretched by amount 5 inches, and that would be the maximum amplitude. So in reality, of course, the x is going to change, right? Because there is going to be friction, there's going to be some sort of drag, there will be losses, and that means that x is going to decrease over time. But the maximum value of the x was achieved when you pulled it to the right? If there's no friction, then of course, in an ideal world, you will continue to go back and forth between the maximum value, which is x sub m, and the minimum value, which would be minus x sub m, but the magnitude is same, right? So going downward below the timeline, you will have minus x sub m. But this is called amplitude. So that's the maximum distance that the particle will go away from the equilibrium. Okay, then we have omega nt here and we have phi over here, right? So since this is actually a sine function, we can also talk about what is the frequency of this sine function and what is the time period, okay? So time period is easy to see over here because we know that this value of x will repeat after you have gone through 2 pi amount of time, right? So sine of something will come back after you add 2 pi to the angle, right? So when omega nt is equal to 2 pi, you will have completed one cycle. So when omega nt is equal to 2 pi, you will get, so we'll call it omega nt tau because we are looking only at one cycle. So we get the time period as 2 pi over omega n. So if you start over here, let's say this is the starting point, and you come back to the same point after one cycle, that gives you the tau. That's the time period, right? Or you could look, somewhere here, at right over here, and then go back, go from here to here. That's also one time period. So that basically tells you what is the distance between the two peaks, okay, or the two troughs of this sine curve on the timeline. So that gives you the time period. So this is called the time period of oscillation. It's a time period of oscillation or vibration, okay? So we looked at the amplitude part, right, which is XMM, that's the maximum distance traveled by the particle. Then we looked at the time period of oscillation, okay. We can also devise what we call frequency, which is defined as 1 over tau, okay, and the unit for that would be, of course, per second or hertz. So 1 over tau defines the frequency. So this is the frequency, okay. Omega n over here is called, so let me write that, omega n is called circular natural frequency. Circular natural frequency. The reason it's called a natural frequency is because the only forces that try to restore the particle back to its equilibrium are the forces that are part of the system. Okay, so in this case, the force that is part of the system is the spring force. All right, and that force is also called a force of restoration because it tries to restore the particle back to its equilibrium position. Similarly, you can have a pendulum where the restoring force would be gravity because the gravity is what will try to bring a pendulum back to its equilibrium position. So at this point, you may ask, okay, so what are the other kinds of forces that may not necessarily be restoring? Well, the forces that are actually externally applied on the system that cause the vibration to continue, and we'll look at those as well pretty soon. Okay, so this is called circular natural frequency because this frequency arises naturally from the system, and it is only dependent on the system parameters like the mass as well as the spring constant. And we have already seen that omega n is defined as square root of k over m. So let me write this again over here. So omega n is equal to square root of k over m. So you can see that if the spring stiffness is larger, then the circular natural frequency will be larger. If the mass is small, then also the circular natural frequency would be larger. So if your goal was to increase the natural frequency for one reason or another because you were trying to decrease the time period of oscillation, then you can do that by choosing your spring stiffness as well as the mass of the particle appropriately. Okay, now phi over here is called the phase angle. It's called the phase angle. If phi is zero, then we know that the sine curve would look something like this, right? It would look something like this if phi was 0. Okay, so this is basically telling you that this is not, phase zero phase zero sine wave. It's a non-zero phase sine wave. Okay, so now that we know what the solution for a spring mass system looks like, the question is, how do we get all these different values like xm and phi and omega n? Omega n is obvious to determine because once we know the spring stiffness and the mass, we know what the circular natural frequency would be. What about xm and phi? Okay, so to determine xm and phi, we need to be given some conditions, either the initial conditions or some intermediate conditions or final conditions. So some of the popular conditions that may be given to you are at time t equal to 0, the displacement is something. Okay, so for example, you take this particle, displace it by a certain amount, and then you release it from rest. So there are two pieces of information given to you there. One is that what was the displacement at time t equal to 0, and the second is the velocity information, right? So if let's say you're given that at t equal to 0, x is equal to, I don't know, some value, let's say x0, then since the solution looks like this, we can substitute at t equal to 0. So at t equal to 0, x is x0, that's xm times sine of phi, right? Okay, so we get that. Okay, now we have to find phi and xm both. Okay, so now let's say we are also given that at time t equal to 0, the x dot, which is the velocity, was 0. So let's do that. So x dot is equal to xm cosine omega nt plus phi times omega n, and that is equal to 0 since omega n and xm cannot be 0, which means that this is 0, and if that is 0, that means omega nt plus phi is equal to pi by 2, right? Because we know that this is going to be 0 for pi by 2. Okay, so this is at time t equal to 0, so that means we have to set this to be 0 too, so we get phi equal to pi by 2. Okay, so phi is pi by 2, you substitute that in here, and that gives you sine pi by 2, so that gives you xm to be equal to x0. So you find that your solution is x0 times sine omega nt, right? That's what you get. So such a system is called a simple harmonic oscillator because you have one natural frequency over here and it's a harmonic function. All right. Now, this is just one example of the kind of initial conditions you may be given. You may be given that at time t equal to 2 seconds, there is certain displacement, there is certain velocity, or at time t equal to 0, it is actually pushed with some initial velocity. So you can substitute for those in these equations, and as long as you have two unknowns and two equations to solve for, then you can solve this problem. Now let's look at the same spring mass system, but from a different perspective. So instead of having the mass move horizontally, what I'm going to do now is I'm going to have the spring mass mounted from a ceiling like this. Okay, so I have the same spring of stiffness K and I have the mass M, and the idea is we want to find out if gravity plays any role or not in this system. Okay, so we'll proceed along a similar line. First thing we will do is we'll find out where the equilibrium is. Okay, so in equilibrium we know that sigma F is equal to 0. Okay, so if we draw the free body diagram, we have the weight, and let's say it is pulled by amount delta static to indicate that the spring is stretched by a delta static amount. Okay, then these two have to be balanced, so mg is equal to k delta static. Okay, so we'll call this equation 1. So let's say this is the equilibrium position. So remember, equilibrium position is not necessarily the position where the spring is going to be unstretched. In fact, in equilibrium position, the spring is definitely going to be stretched so as to balance the weight of this particle, right? So from equilibrium, again, we will choose a positive x direction of movement. Let's say we displace it by amount x. Then in this position, you again draw the free body diagram. You have the weight, which does not change. But now the force from the spring is going to be k times x plus delta static. Why plus delta static? Because at equilibrium, it was already stretched by amount delta static. And then from equilibrium, we displace it by amount x. So the total stretch is x plus delta static. Okay, and the downward direction is a positive. So now we'll write sigma F equal to ma. So this would be mg minus k x plus delta static equal to m times x double dot. Notice I'm not writing I hat anymore because this is a 1 degree of freedom motion, right? There's only one parameter required to describe the position of the system. Okay, so we get that, but we also know that mg is equal to k delta static. So these two terms actually cancel, and we get mx double dot plus kx equal to 0. We'll put it in the standard form by making the coefficient of x double dot to be 1. So this becomes k plus mx equal to 0. We already know that k plus k over m is omega n squared, and that is equal to 0. So we get this exactly the same equation that we had before when the particle was attached to the spring and moving in a horizontal direction, right? So this equation of motion is exactly the same. So we call this particular differential equation describing a system which is called a harmonic oscillator. Okay, so for a harmonic oscillator, you always obtain a differential equation which describes the equation of motion, which is in this form. Okay, that's how we define a harmonic oscillator.